Okay, so we're talking about honors homework problem 26. Okay. A uniform ladder of mass m and length L leans at an angle against a frictionless wall. So on the wall, friction is 0. Okay. It's fine if that point's there. There's an angle theta. They say the length of the ladder is lowercase l. Sure. A frictionless wall, the coefficient of static friction between the ladder and the ground. So now I do have the point where the ladder touches the ground. We have a mu s. I have to say greater than 0. You don't want to know about where friction could be negative. Pretend that's not a thing. Okay. Determine a formula for which the minimum angle at which the ladder will not slip. Okay. There's no friction on the wall. So let's first torque analyze this equation. So why the only thing stopping it is right. There'll be a friction force on the wall on the base of the ladder pointed to the right, and the wall there will be a normal force from the wall resisting any motion. Right? But if there was no friction anywhere, the ladder would just whoosh, slide down the wall. Okay, we could try it with a meter stick and make it slip. Oh, the carpet's really. I could try it like over here. If I lean a meter stick up, oh, it doesn't slip at first, but if I make it really shallow, it falls down. So what's the angle? Okay, for all these questions, we just kind of have a little faith. We set up our 3 equations. There are really just 3 equations for chapter 9, so I didn't give an equation sheet. What are they? There's 2 equilibrium equations. Sure. Okay, he's got the hard one right away. Torque, which is a vector, is equal to lever arm, which is a vector if you want, times the force that's producing the torque, and I have them in magnitudes there, times the sine of the angle between them. Okay. Good. Just like, so you couldn't completely succeed unless you remember that elastic and inelastic had to do with kinetic energy. You can't misunderstand what lever arm is. So hopefully this example will demonstrate it a bit. The other 2 equations are conditions for equilibrium. If I'm in equilibrium and don't slide down the wall, they're very simple equations. What has to be satisfied? Okay. The sum of the forces in the y direction have to be 0. And why not x2? Sum of the forces in the x direction. I consider that's one equation. The sum of the forces in each direction. Otherwise, we would accelerate up, or we would accelerate down. Okay? I didn't get my wheel out. We can pretend I have a wheel. Okay? At this point, I should hold up a bicycle wheel and exert forces on it, left and right. But then I show you I can still have force on it, and it doesn't accelerate left, right, or up, or down. It just spins around. Okay, so if we're in equilibrium, we can't be spinning either. And that means the sum of all our torques, and they are vectors. Okay, sum of all the torques equals 0. Very good. All right. Any questions so far? Okay. Let's see. we forgot. So the ladder has mass little m according to the problem on our homework sheet. Where is that mass located? Sure, Christine. Right, okay. It does exist, of course, throughout the object. But good old Isaac Newton, maybe not so good, invented calculus and proved that you can consider the mass to be right at the center. Okay. So, let's see. Maybe I should draw this mg straight down. Okay, and if you want, I'm going to start to add some colors here. Okay. What will counteract mg? So, I'll have forces in the y direction, and they better add up to 0, and I have minus mg. What supports the ladder? This will be a normal force from the floor. Let's give that one the original normal force name, F sub n. Okay, draw that, because there's going to be a normal force from the wall, and it needs a different name. And now there's no other forces, because there's no friction against the wall, so that wall up there, only the floor. The wall can't push up or down, it can only push left and right. Okay, well, I'm going to write one at the bottom. 2 and okay. Oh, well, fantastic. So I know that since there's no other vertical forces, the magnitude of the normal force must be mg. The full weight of the ladder is supported by the floor. In the x direction, let's make this so it better be perpendicular because it's a normal force. Let's call this Fw for F wall. The wall pushes the ladder straight out. Not hard enough to like throw it off, but it stops the ladder from like falling through the wall. If I hold up a meter stick at an angle, it wants to swing down and crash, especially if there is some friction here at the bottom. Okay, so and that one points left. So I have minus Fw. Not sure how much that is. And then to the right, I have a friction force from the floor. Do that F sub F real small. What's the friction force from the floor? Do you remember way back? Just have a thing resting on a flat surface? Sure, Christine. Okay. Force of friction has to be mu times normal force. That's right. That's what I want. I might as well just write mu times mg. Because I already figured out the equation right above it that normal force is equal to mg. Because we're in equilibrium here. And it's mu times normal force, so there we go. Okay, I got the force from the wall. Oh, but that mu that's what I'm trying to... Oh, no, it's not what I'm trying to find. I'm trying to derive some minimum angle. Oh, man. Derive the formula for the minimum angle at which the ladder will not slip. Okay, so without torques, this is actually a pretty easy problem. But I don't know anything about the angle. Ready for the real fun to begin? Okay, and we got maybe 5-6 minutes. Alright. Sum of the torques has got to be 0. Oh no. Before I can even measure lever arms, what do I have to do? The lever arm is like the perpendicular distance between the force that's causing a torque and yeah, the axis. Where do I put the axis? Lucky for us, it's an equilibrium problem. So the truth is, wherever I want. where do you want to put it? Where it's a reasonable place, so I can see 3 points that make any sense at all. Sorry? We could put it in the middle. I kind of don't want to though, because gravity is going to be one of the easier forces. Where do I have the most forces? And we can always try it different ways. Yeah, let's do the bottom. Let's do the very left. Let's put our axis on the floor. Okay, because if it's actually stuck to the floor with friction, that's realistic too. That's where it's going to pivot around anyway, naturally, hopefully. Okay, even though it's equilibrium and it doesn't pivot at all. Okay, so here I have the wall. Oh no. Okay, so is that going to be a positive or a negative torque? Force from the wall pushes on the ladder. Do you remember? Counterclockwise is positive, just like the angle is swinging up from the x-axis. Math class override. So it's plus, and the lever arm is L, the length of the ladder. The magnitude of the force is Fw, or I could put mu mg. Let's save our writing. And then I need the sine of the angle between the ladder and the thing. Is that theta? No. It's like 180 minus theta. There's probably a better... You can start looking up trig stuff when I'm done with my example, but probably a better way to do that. But here, theta is between the ladder and the floor, and F wall is parallel to the floor but in the opposite direction. So that makes sense to me. 180 minus theta. Ooh, there might be some fun sine thing in there. Okay, and then I better have a negative torque to balance it out. Okay, sure enough, I do. I have minus, it's L over 2 because I'm at the center of mass, and my force is just mg. And then I have the sine of another silly angle. It's not theta either. It's theta plus 90. Oh no. Well, okay. Actually, because that has mu and that has that, and there we go. If we can solve for theta, oh dear. Okay. And so we'll need, we need theta at least as steep. Greater than or equal to what? Perfect. Okay. Do you know some shortcuts with sine and... Okay, because theta is the angle between the ladder and horizontal, and then gravity points straight down. So we just go out the end of the lever arm, and then we swing, we measure the angle to where we go. Okay.